Hello everybody, my name is Gomonay. I am from University of Mainz and today I will talk about antiferromagnetic spintronics in materials with magnetoelasticity and especially with the strain gradients. When we discuss magnetoelasticity in magnetic materials, we always imply some homogeneous strains which appear due to the phase transition and magnetic ordering. These strains are directly coupled with orientation of the magnetic vector, in case of antiferromagnets the Néel vector, and these strains can modify magnetic anisotropy and also couple magnetic system with the external stresses, thus allowing switching by stress or strains. However, in spintronic devices, we usually face with the gradients which are created, for example, due to the current flow. Current creates temperature gradients which unavoidably create also the gradients of strain. These gradients could be much larger compared to the values of strains themselves. So the question is whether these strains can be coupled with the magnetic ordering, contribute into magnetic anisotropy, and whether the magnetic texture creates these additional strains. In other words, in this talk, I will address the question whether the strain gradients can give us new functionality for the very effective manipulation of antiferromagnetic states. So, today I will talk about strain gradients as the effective tools for control and manipulation of antiferromagnets, and I will also introduce a gradient magnetoelasticity model, the effective model for description of antiferromagnetic textures. In my talk, I will introduce some basic concepts of incompatibility and strain theory, and then give two illustrations using as an example thermomagnetoelastic effects and magnetic textures in the devices with different shapes. So, magnetostriction is usually considered as deformation of the paramagnetic state when the system goes through the phase transition point, and corresponding strains are called spontaneous strains, and they are coupled with orientation of the Néel vector. However, if such transition takes place in inhomogeneous material, for example in antiferromagnet grown on a non-magnetic substrate, then deformations of two layers would be different, and this induces so-called incompatibility of strains. Another example of incompatibility is given by the two domains of a magnetic material with different deformations. At the interface between these two domains, the different strains or difference in strains can also induce incompatibility. Incompatibility appears always in case of inhomogeneous distribution of spontaneous strains, and mathematically it is expressed using the gradients of spontaneous strains. Incompatibility is a well-known concept in the standard elasticity theory, and it is usually used for description of the materials with the defects such as dislocations and disclinations. If, for example, we cut a piece of a material as shown in the top left picture, and then we'll try to restore continuity of the sample, then the strains which unavoidably appear due to this process are called plastic strains, and they could be calculated from the equation, Poisson-like equations, where incompatibility plays a role of a source. Such equations and their solutions are well known, but the main problem of such approach is that incompatibility in this case should be introduced as something external, based on atomistic calculations of the lattice structures. However, recently several research groups from different places, I give here only some of the names, Lazar, Sharma, Osipov, Malyshev, they suggested technique which allows regularization of this problem. In other words, these equations of elasticity theory in presence of the defect could be formulated in terms of Lagrange formalism, and in this case we need to add gradient terms in strains into description of the system. In this case, we have, instead of singularity which is introduced in the equations externally, we have self-consistent system of equations, and the information about the defects is coded in the terms with gradients, while the rest of the terms describe plastic deformations. In application to magnetic or magnetoelastic material, the natural way to generalize this approach is to introduce gradient magnetoelasticity, which I am going to discuss and present in this talk. The idea is very similar. If we have a material with inhomogeneous distribution of magnetic vectors, then due to spontaneous strains we have incompatibility, which is again related with the magnetic ordering. So instead of calculating separately incompatibility and plastic deformation, we can introduce Lagrange function which includes gradients of strains and the magnetic vectors, and these gradient terms will be responsible for the magnetoelastic defects. And what is very nice, now the equations would be continuous and could be analyzed also from the point of view of topology. So let's look at several examples where this magnetoelasticity can be helpful. I will start from the basic example where the magnetoelastic terms both include gradients and coupled as shown in this slide, and this kind of terms could be responsible for the creation of vortices, coupled vortices of magnetic and elastic subsystem. So let us consider a sample in which 4 domains meet together. You see the scheme where the joint point of 4 different domains is circled. If we look in details with high resolution of this junction point and look at the distribution of the Néel vector, then we see that the Néel vector rotates around the circle, and in this way we have magnetic vertex. However, the blue ellipses in this slide show corresponding spontaneous strains which should follow magnetic ordering far from the junction point. So this means that not only a magnetic system rotates and whirls, but also it should be some non-trivial distribution of strains as shown here. Blue arrows demonstrate distribution of strains which are presented in a very special way. The components of the arrows corresponds to the strains as shown at the side pictures. So if we look at the circled area which corresponds to the junction of 4 magnetic domain, we found out that this point is also a center of the strain vortex, and the strain also rotates through 360 degrees, similar to the magnetic vector. This type of the strain distribution is known in elasticity theory and corresponds to dislocation. These magnetoelastic disclinations were introduced by Kleemann and Miltat for ferromagnetic materials based on the considerations of old elasticity theory, but gradient magnetoelasticity allows to predict such solutions in a regular way. This was a relatively academic example, but now I would like to discuss another example of gradient magnetoelasticity, which is very helpful in applications. In this case, I will discuss additional magnetic anisotropy, which is created by gradients of isotropic strains, which are associated with the volume change. Such type of effects can appear due to the current-induced switching in antiferromagnets. In mines, we studied switching in nickel oxide, and we found out that the current-induced switching cannot be explained by the spin-orbit torques only. So then we suggested the thermomagnetoelastic explanation for this effect, and this effect is a good illustration how the strain gradients come into play. So let's consider a standard hole cross device where the current flows from left to right electrode. In the cross region, the distribution of current density is highly anisotropic with hot spots as shown in the left panel. Such inhomogeneous distribution of current density creates inhomogeneous distribution of temperature simply due to the Joule losses. And what is more important, the temperature distribution is coupled with the volume effect. So the lattice is expanded and the expansion is proportional to the temperature variation. However, such expansion is isotropic and cannot remove anisotropy or add to contribute to the anisotropy of the system and induce switching. However, the temperature and correspondingly this isotropic strain is distributed highly inhomogeneously, as shown in the right panel, where we show the temperature gradients. So in this case, such temperature gradients are responsible for creation of other strain components, uxx minus uyy, which can contribute into the magnetic anisotropy and induce switching. How this coupling appears? This I will try to explain in the next slide. So let's look at the region of the sample where the temperature gradient is relatively large. In this case, the hot and the cold region of the sample would be expanded in a different way. A lattice expansion is shown here by squares, and the lattice, the edges of these squares is different. At the interface between hot and cold regions, these strains are not compatible. In other words, gradient of such isotropic strains induces additional anisotropy in the system, and as a consequence, additional strains shown as ellipses. If we integrate over the whole region where such strains appear, we find out that in the center of the cross, the average strain is anisotropic, favoring certain direction of the Néel vector as shown in the right panel. In other words, in homogeneous volume strains and create additional anisotropy field, which is equivalent to the external field and induces switching of the states. This video shows how such switching takes place in the center of the cross due to the current. In order to prove that the mechanism which we observe during the switching in our devices is related with thermomagnetoelastic effects, we first calculated the distribution of strains in the devices for different current directions, and we find that depending on the direction of the current and configuration of the current, the switching can be either parallel or perpendicular to the current direction, which excludes the mechanism based on spin-orbit tops. To go further, we made a device with the hole in platinum electrode. In such a way, we excluded directly the magnetic interaction of current and localized spin. In such a system, we still see switching between different states, which confirms the thermomagnetoelastic nature of the effect rather than spin-orbit origin. And then the switching takes place like shown in this video. Now I would like to give the third example, and this is more a prediction of what we can anticipate in different shapes of our antiferromagnetic devices which we usually use. So in this case, the additional contribution to the energy appears due to the magnetic gradients, which are also coupled with distribution of strains. So let us consider an antiferromagnetic sample cut in a rectangular shape in such a way that the edges of the sample are parallel to the easy magnetic axis. here in this slide you see a distribution of the Néel vector calculated in neglection of magnetoelastic effects. So in this system we can anticipate three-domain state with the domain walls, and the distribution of the Néel vector is quite symmetric. However, if we take into account magnetoelastic effects, then the corresponding distribution changes in such a way that strong asymmetry between up and down becomes quite pronounced. Similar asymmetry is also observed in distribution of strains. This asymmetry in the domain wall width can be explained by the effects which appear at the corners of the sample. We assume that at the surface of the sample, the Néel vector tends to be aligned parallel to the surface due to some additional surface anisotropy. So, in this case, the Néel vector in the corners should rotate through 90 degrees while going from one edge to the other. And due to magnetoelastic effects, such variation of the Néel vector induces corresponding variation of strains, as shown by ellipses. What is interesting is that this orientation of the strain is different in the left and the right corner. Such distribution of strains correspond to the partial disclination, and the sign of the disclination in the left and the right side is different. So, in this case, in the right corner, the distribution of strains favor orientation of the Néel vector along the ellipse, along axis of the ellipse, while for the left corner, the preferable axis would be 90 degree rotated. And this creates asymmetry in a distribution of the Néel vectors and the effective width of the domain wall. Such partial disclinations affect also the growth of the domains, and this could be seen in the other example. So instead of cutting the sample parallel to the easy axis as shown here, we now cut it in such a way that the edges are parallel to the hard axis, and the Néel vector tends to be oriented at 45 degrees with respect to the edges inside the sample. In this case, partial disclinations which appear at the sample corners favor creation of different orientations of the Néel vector, gray and red in the left panel and yellow and dark in the right panel. So in this case, the domain structure will grow starting from the edges, and the orientation of the corners imposes the certain type of domain which grows. With this, I am at the end of my talk. So I introduced the concept of gradient magnetoelasticity, which can be very helpful in prediction of different structures and textures in antiferromagnetic system. I demonstrated that this gradient magnetoelasticity can describe thermomagnetoelastic effect, which is responsible for switching in antiferromagnets due to the current, and also illustrate the application of magnetoelasticity to the prediction of textures in different shapes. This work was inspired by experimentalists and by collaboration with fantastically interesting people from the University of Nottingham and from Matthias Glaube group in Gutenberg University of Mainz. Thank you for your attention.